What day is your? And then and then I'm thinking. So that one, you'll do fine. Yeah, I'm sure I'm fine now. So the 3 labs.
That was actually, yeah.
All right, y'all. Howdy, howdy. So we are near the end, y'all. We have today, Wednesday, Friday, and then Monday. So we are nearing. It's kind of like the last week. You count today and a week today. Today we'll easily finish the last step to teach you, and then we'll naturally just roll right into review. Regarding the review, y'all, there's going to be no graded clicker so Wednesday, Friday is coming Monday. Sure, I'll be doing stuff. You're still paying me. I'll still be here reviewing all that stuff. But you ultimately decide. There's no clicker questions. I'm not going to give any. I may have questions, but they will not factor into the final grade. So I may still have people responding to them. They may still get sent to your all's devices and stuff like that, but they will not count to the final grade. Okay, so that's really important. Because we're in the review part, so you do whatever is best for you in the review. I'm not covering anything new, but I will be kind of going over, hey, here's the things to keep in mind. Here are the questions that were missed on test 1, test 2. You can expect to see examples of those. Otherwise, one of my recommendations for you all. So remember, on web courses, we still have the reviews I posted before. Test 1 review, test 2 review. Those are just as good for the final as they were for the other tests. So I'm not going to make a new review for kinematic. I'm not going to make a summary of what was in kinematics and momentum and energy and forces because I've already made those. You already have access to those. So I will make a review, hey, here are the main points for angular momentum, things that go in circles, things we've covered since test 2. But any other kind of summary is already existing in your own thing. So I'm not going to make another cover of that. But I will solve problems in those categories.
What's the ratio between new material and old material?
Yeah, so the question was, what is the ratio between new material and old material? So there's been about 11 weeks of content. There is 47 questions, which, do the math, 47 divided by 11, it's about 4 questions per section. Maybe 1 or 2 sections will have 5 questions. I honestly don't remember which ones have 5 questions. So every section is equal. Every week of content, that's how I designed a test. I did week 1 and I made 4 or 5 questions for it. I did week 2, I made 4 or 5 questions for it. Week 3, 4 or 5 questions for it. Until at the end I had 47 questions. Yep. So minimum 4 questions, at most 5 from each week. So equal weighting to every week's worth of content. Again, it's 47 questions, which seems like a weird number. That's just kind of where I landed on. I kind of had made, so basically I made enough questions for every section. So I made 44 questions, 4 times 11. And then there was a few questions I wanted to add, so I just chucked them in there. And we ended up with 47. So, should be a nice, I went through it. I've checked it 4 times now. Should be good to go. I sent an announcement about this, and I'm going to be reminding almost every single day, it's like a broken record. Our exam is Friday, April 26th from 4 to 6:50. Not 4:30. Not 4:30. It is 4:30 right now. Our exam will not start at 4:30. No matter how many times I say this, I will still have people who don't realize that it starts at 4. Set a reminder on your phone. Do what you need to do. If you miss this exam and you do not fall under the excusal policy, it's going to be a sucks to suck situation. The reality is I can't have a million people doing makeups. I can only do makeups for those that have things that fall under the excusal policy. This is one of those things in life where if you miss it, It will not be good to you. Your highest grade you get in the class, this is 20% of your grade. If you miss this, literally the highest grade you can get in the class is an 80, and that's assuming you got a perfect score and everything up to this point. This is probably true, this is pretty much probably true of every single class you take here at UCF. The final, now again, the final is super important. Can't stress that enough. Make sure you're here. Make sure you bring calculator. Make sure you bring your note paper. This is one of those things where if you're stressed about the test, I hope that the only stress is that, like, okay, you gotta make sure they get here on time. I don't want you stressed about the sure, stress happens, stuff like that. The test itself, you all should be totally ready for. Just don't miss it. Set like a million alarms or whatever. Do what you gotta do. This is just one of those things in life. You will have these things. You have an interview for a job, you better be at that interview. You miss the interview, that you're probably not gonna get that job. You will have these things in life outside of school. Sometimes it just goes that way. So, now I said that if you have something that falls into the excusable policy, a sickness, get a doctor's note kind of thing, contact me, we'll talk. An unexpected family death, send me a message, we'll figure it out. A school-related, like a thing that, like you're in a sports team or something like that, whatever it may be, and if it's something you know, so let me know sooner than later. Because the reality is, I have a single day scheduled for makeups that fall into the excusable policy, so it's better I let you know what that day is sooner than later. Because it's 2 hours and 50 minutes that I show up here. Like, I don't want to have a bunch of makeup days. That would be a lot of time of me sitting around. Anyway, there's that. So yeah, hammer that into your head. Student reception instructor, really appreciate if you do that. Yada yada. That's closing, I think this Sunday or something. I don't know. It said 15 days when it posted, and that was like how a week ago.
Will it be the same way, multiple choice, like you'll provide the Scantron?
Yes, so the test will be 47 questions, first 2 pages, front and back will be all the questions, third paper will be a blank paper, fourth paper will be the Scantron. Yep. It had been sent as of 30 minutes ago to be printed, so yeah, it is made. But yeah, you all, and then yeah, just make sure it's the same other policies. Really good question. Scantron will be on there. I tried to make the Scantron a little smaller so you didn't have to bubble, take as much time to bubble. I don't know. Hopefully it's a lot better. All the formulas are on there. The formulas are copy and pasted from that last formula sheet, so everything's there. Okay, any questions about this? All right, you all, I extended, so let's just look at your all's assignments for the end of the year. Make certain again, we finished strong. So I believe, and I'm going to double check this right now, that you all have one more discussion due this week. It's your last discussion. So my to-dos look a little different than your to-dos. In fact, actually, let's just go back to this to-do because it's had them all nicely organized. All right, so at the front, scroll. Look, y'all, we're here. We made it. So yeah, you all have one more recitation. That's this Friday. And you have the quiz. So quiz 10, you all have until Wednesday to do. And then the last quiz, I gave a tiny little extension to quiz 11 on angular momentum. We're finishing up everything today. You have until Monday at midnight, so a week from today. This is the last quiz. Do not skip the quiz. It's really stupid too. I can guarantee you will get a higher score guessing than you will by skipping it. You got 1 4 shot on those questions. So. Make certain you all do these. The lowest quiz grade is dropped. Yeah.
Then can we skip it if that's on the lowest quiz grade?
Only skip it if you got perfect scores in all the other ones. But even then, I still recommend doing it just to see the type of questions you might expect in the final. If nothing else, it's good to do, so the lowest quiz grade is dropped, unless you've gotten perfect 5s in every single one, there's a chance you get a 5 on this, so it can improve your grade. But more importantly, the reason I give these, definitely do it so you can see the type of questions to expect in the final. It's better to miss a question on this than it is on the final. So, the whole point of these quizzes is for you all to be able to test, do you know what's going on? The more aligned you are to taking this quiz the way to the test, so if you have someone just solving the problems for you, it's absolutely useless for you as a learning tool. So make certain you all, at some point when you look through these quizzes, that you're looking at it yourself. Because it's a similar difficulty level to the final. All right. This is a little bit more difficult, I suppose. Meaning, if you can do this, you can do the final. I always make the practice harder than the real deal. That's a good strategy in life. Okay, last thing. Sometime this week, I have no idea when I'm going to send this out. Sometime this week, I'm going to make an Excel document that lets you input all your grades for each section to see kind of like, because the classic question is, remember, at the end of the year, very, very end, like after everything is graded, I will calculate your grade with and without quicker questions. So to that end, I will make an Excel document that does that for you to let you see what your grade looks like with and without quicker questions. You can play around. It's kind of like, I think this thing has a thing where you can play around with your grades and see what you get if you had this grade, that kind of thing. I will make one of those in Excel that lets you do that without the clicker questions included as well, with and without. So you can kind of play around and see what it would be. I'll put like the logic in there where your test grades, so if you get an 80 on the final, if that replaced your lowest test grade, whatever. I'll put it in so you can play around with the numbers and see what you need. Shouldn't take me too long, but when will I get that done? No idea. Sometime this week. I'll send it out. Try to make it nice and pretty.
The end of semester, the theme for like the extra point or two is due April 19th.
Oh, yeah.
That's still up, like, it's still applicable.
Yeah, did they send out anything about that yet?
No, I was so curious last night, so I was like, oh, did I miss the deadline?
Yeah, okay, so there should be some end of semester, I think, assessment. I need to check into that. Would you mind sending me an email about that? No, whatever. Alright, you all did a pre-assessment thing way at the beginning that was worth some points. There should be some post-assessment thing, I think. I have to double check. Yeah, so I'll shoot me an email and I'll look into that. Because that's like in a separate web course thing, so I never even see it when it pops up. But I do want to look into that. Okay, and the last announcement, I posted all the test grades are done. Like the test 2 grades, the pre-response are all in there. I sent out an announcement about that. The average was a 71 point, I don't know what, something. I'm pretty happy with that. I did not curve it because it's already in the thing itself, because it's partial credit, there's kind of that built-in flexibility. And I'm 71%, I'm pretty happy with, to be honest with it. That's solid. It may not sound solid to you, I don't know. But I'm happy enough with that. Obviously, some of you did better. Obviously, some of you did worse. 71%, I'm pretty happy with. So it stayed as is. Those grades were in there. Free response was scaled to 40. Multiple choice was scaled to 60. And yeah, so it's all there. Overall, very happy. Great job, y'all. I graded a few myself as well, and they looked pretty good, so. All right, any final questions before we finish up the learnings? All right, y'all, let's finish up rotational stuff. So, last class, what did we do last class? Last class was all about Newton's second law for rotation. Torque equals I alpha. So this is what we basically focused last class. Torque was like force, I is like M, alpha is like A, and so a net torque results in a net angular acceleration. We talked about that toy my wife got for me for Christmas. What a cool toy. Highly recommend them. They're on Amazon. Kids love them. I don't know if I'm an advertisement for it, but they do break easy, I guess. Don't chuck them. That's how mine broke. The battery got disconnected, couldn't fix it. Very sad. Yeah, and then we did a problem with it where we basically had two things applying torque to an object, and we said, which way is it going to rotate? Which way is it going to angular accelerate? What's the value? And it wasn't too bad. It looks like a lot, but this is the entire problem. If a problem takes only this much space, it's not bad. When a problem takes an entire sheet of paper, then you're talking. So math here wasn't too bad though. Great one for y'all to work through. All right, cool. Then we talked about angular momentum. It was like regular momentum, but L instead of P, I instead of M, omega instead of that, and tricked a lot of people with this one. If you have two things with the same mass and radius, a solid sphere and a hollow sphere, the one with the hollow sphere will have a higher angular momentum. because it has a higher moment of inertia. All right, great. On to new and exciting things. So the first question, a figure skater. You all have seen figure skaters. If not, it's the people on ice. You know, they do the classic spin move. They spin in a circle. And the question to y'all, they start with their arms out. You know, it's a classic thing. You know, like a ballerina. They start with their legs out, their arms out, and spin. And then they bring their arms inward. What happens to their angular momentum? What happens to their angular momentum? Not angular velocity, not angular energy, not rotational energy, angular momentum. In fact, I'm going to be so kind and I'll even put the equation for angular momentum up here. It's that weird symbol. I do not want to reuse that slide. Get out of here. L equals I omega. What happens to their angular momentum? We'll find out. Depends. What's a trick question?
Everything is.
What's a trick? Yeah. It's a good question. It's a segue into the next thing I teach you is what it is. All right. But it is tricking people. Ooh, what does that mean? Who is it tricking? I don't know. Some amount of y'all. All right, we'll close it in 5, 4, 3, 2, 1. All right, so to talk this through. So I could just show you the next slide and tell you the answer, but we could derive the next slide. So let's model this figure skater like a cylinder. They're basically a cylinder, right? Yeah, basically, you know, a person is their arms kind of mess things up a little bit. But when you're standing, you're kind of a cylinder. And let's just pretend like the arms, we can model this cylinder. We love to model things. So what's the I for a cylinder? I'm double checking because I don't want to be a fool and accidentally mess it up. Where are you at? Slide with all my moment of inertias. All right, so a cylinder, i.e. a figure skater, mr squared over 2. That's my beautiful cylinder. All right, just like this beautiful ballerina. Or handsome. You know, it doesn't really say. I say ballerina, figure skater. Could be a guy, could be a girl, could be anything. All right, mr squared. Great. So looking at this equation, we say 1/2 mr squared. And if they bring in their arms, we're like, oh, R goes down. But we need to remember that omega. So remember, y'all, that V equals omega times R. Let's go ahead and rearrange that. Omega equals V over R. So boop, boop, boop. We're going to put that in. 1/2 mr squared times V over R. All right, and I'm feeling like an R's needs to go away somehow, but not quite sure how that's going to happen. That didn't go exactly how I was hoping. I was hoping the R would cancel out. All right, yeah, I was hoping. I'm going to have to look into that. I was thinking, oh, it's squared, so the R is going to cancel out. It doesn't quite cancel out, but it should. I'll tell you all why in a second, but I'll have to look into the math why exactly the R didn't cancel out the way I'd hoped it would. Because you're like, oh, it kind of did, but not quite. Sad. All right, I'm going to look back at this. My explanation didn't pan out the way I hoped it would. Disappoint you all. The angular momentum stays the same. Yeah, again, I'm going to double check and I'll look into where the extra R, how to derive the canceling out. So conceptually, I failed. Mathematically, I failed, so I'll come back to that. Remember, y'all, here's the easier way conceptually. Momentum is conserved. Angular momentum is also conserved. That's the conceptual understanding here. So y'all remember way back when that your initial momentum equaled your final momentum? The sum of your initial momentum equaled the sum of your final momentum. If you don't remember that, great thing to look at. Yeah. Oh, yeah, no, go ahead. Yeah, so angular momentum is going to do the same thing. That's the next slide.
So if it stays the same, then why do they put their arms in? There has to be a reason for it.
Yeah, so I got to look into how to cancel out that r, because originally when I was thinking through this, I was just doing it in my head, and I was like, oh, omega squared, and that'll cancel it out. Yeah, omega's not squared, so it didn't cancel it out the way. So I'm going to have to look into that. I'll tell you all Wednesday. My initial reasoning coming into class, I just didn't write it out. My bad. That's why you should always write out your math. Because if you do it in your head, you make stupid mistakes like I do, where you're like, oh, omega squared. No, it's not squared here. But yeah, for now, just trust me. Well, okay, you all know momentum is conserved, so this is just a very small step. Momentum is conserved, put the word angular in front of it, and it's also conserved. But mathematically, I'll prove it to you all next time. Maybe just the way I was writing it out didn't work out the way I wanted. Angular momentum is conserved. Angular momentum is conserved. So, and you all have experienced this. If you haven't, go sit in a spinning chair. Bring your arms in, you spin faster. Put your arms out, you spin slower. It's a classic physics demonstration where usually we'll have a chair up here and have someone holding some weights and do that. But hey, you all got spinning chairs. Oh, sure. I don't know how well this one spins. I do have a spinny chair. I don't know how spinny it is, though. I mean, it's got to spin well, so I'll test. Oh, that's terrible. It's too damped. You need one that's not super damped, otherwise you can't. Damped meaning it's so I spun it and it slowed down too quickly. You need one that spins pretty good. But yeah, you all got spinning chairs at home. Spin yourself real quick, bring your arms in, you'll spin faster. Or, just, you can just spin yourself. It works just as well. So do it on your own time. You're welcome to do it during class as well. Somewhere. But yeah, angular momentum is conserved, y'all. Things that rotate when they bring their, this is why they do that. When a ballerina or whatever is trying to spin, they kind of put their leg out, they build up a lot of, they build up the angular momentum, and then they bring it in, and then they spin really quick. It's that deep. They are making their moment of inertia go from big to small. As moment of inertia goes down, angular velocity goes up. Because remember that L equals I omega. So if I goes up, omega goes down. If I goes down, omega goes up. They counteract each other. Because it's got to be conserved. We'll do some problems with this. So, great problem. Good one to think about. Great concept. Super relevant. I'll have to think about this, but I'm trying to think if I can make a connection with gears in a car and different gears and stuff like that. I don't know. I don't know if I know nearly enough about how a car shifts to justify that explanation, but all right. So yeah, we already answered this. Figure skater spinning in a circle with her arms out. She brings her arms in. What happens to her angular velocity? It's very subtle, very subtle. Yeah, it looks like the same question, and honestly, when I was reading through it today, I also originally, I was like, oh, did I put the same question twice? What happens to angular velocity? Oh. That's because I did copy and paste the problem, but I changed one word. Work smarter, not harder. No need to retype something if it's the exact same, but one word. Angular velocity. And yeah, this is a good point to go. When you're doing your final or any test, be very careful. Write stuff out, things like that, so you don't accidentally mix up what the words are. Don't assume. Read carefully. It could be worse. You could be a lawyer. Lawyers have to read papers and papers very carefully, every single word. My brother's a lawyer. I don't envy him. I don't know how you have the focus to read that detailed. Every single word. Most of the words matter in a physics problem, not every single one. And I say most, maybe 30% of them. It's way less. Alright, how we doing? Oh, we're doing so good, y'all. My ballerina technique must have done it for you. Alright, we'll close it out in 5, 4, 3, 2, 1. Okay, and this one mathematically is much easier to show. What happens to angular velocity? L initial equals L final. So I omega initial equals I omega final. We are going to model this person like a cylinder again, because why not? So I 1/2 mr squared initial times omega initial equals 1/2 mr final squared times omega final. So let's just go ahead and look what happens. In this case, let's say their radius halved. Let's say their radius halved. So I have my initial radius here. That stays the same. And I have my initial omega. And then my new side, I have r initial over 2 squared. So I'm just making up numbers, y'all. I'm saying if r halved. They brought their arms in. Let's just get like hey, how fast would they end up going? All right, the 1/2s cancel. The m's cancel. Let's go ahead and make this a little nicer. R initial squared omega I equals 1/4 R initial squared omega F. The RI squareds cancel. What does this say? It says that my initial is 1/4 the final. Now, you may look at that. You got to, again, be very careful with these, y'all. A lot of people are tempted to look at this and say, does that mean that the final is smaller? No, the final is not smaller. Let's rewrite this another way. This says that the omega final is 4 times the initial. If you half something's radius, I modeled this as a cylinder. I could have modeled this person as a sphere, a disc, a cylinder, like literally anything. If y'all look at the moment of inertia, they're all r squared. Every single one of them. It doesn't matter what I modeled this person as, the same result would happen. Basically, every single moment of inertia is the radius squared. So if this was a sphere, a cylinder, a disc, a hollow sphere, a solid sphere, empty, who cares? They get 4 times faster. They spin 4 times faster, which is kind of cool. Kind of nifty. All sorts of practical applications of this. If I just modify the moment of inertia, I can change how fast you're spinning. So many ways you could use this. Can I think of any off the top of my head? No. But I need to look into some, because I'm like, anytime you can manipulate something and change something else, that's really powerful. Especially when it's like this. I half the radius and I get 4 times angular velocity. That's useful. All right. Let's do some math with it. Let's do a more involved problem. We are on the second to last slide, y'all. Look at that. When I get to this one, we're on the last one of the entire class. Absolutely wild. All right, so a cylinder. This problem has so many words, but it's a pretty simple problem. A cylinder with rotational inertia. You didn't even know it was a cylinder. I gave you the rotational inertia, the moment of inertia. 2 kilograms times meters squared. Yeah, you gave you the variable for it. Oh, what a kind problem. I1 is that it rotates clockwise by a vertical axis through a cylinder with angular speed omega 1 equals 5 radians per second. The second cylinder with rotational inertia I2 equals 1 kilogram meters squared rotates counterclockwise about the same axis with angular speed omega 2 equals 8 radians per second. If the 2 cylinders couple, that means they originally were separated and then they come together. A good example of this is a clutch. Your clutch, when you release if you have a manual car, the clutch separates 2 spinning discs. When you release the clutch, they come back together and they couple. That's an example of conservation of angular momentum when those 2 things kind of couple back together. If they couple, so they have the same, because they're now stuck together, we have a kind of a collision, right? Kind of like momentum, what rotating things. So they have the same rotational axis. What is the angular speed of the combination? What percentage of the original kinetic energy is lost to friction? That second part's going to take us a little bit of time, but it's all right. We can do it. I say a little bit of time. It won't be bad. All right, y'all. Classic. All right, just to show you all, here's the picture. I have a disc rotating. I have another disk rotating. This disk is rotating clockwise. The other disk is rotating counterclockwise. Immediately you can imagine when these things come together, they are not helping each other, they are fighting each other. That's an important thing to remember. All right, so we have I1 is 2 kilograms dot meter squared. Omega 1 equals 5 radians per second. I2 equaled 1 kilogram meter squared. And I'm going to make a decision. I'm going to decide to do this now versus later. Should omega 2 be positive or negative? If I defined omega 1 as positive and that was clockwise, take a guess around omega 2 if it's counterclockwise. We're going to make it negative, y'all. They're opposite directions, like velocity. To the right is positive, to the left is negative. Remember when y'all did conservation momentum? That was something you had to consider. When you did conservation momentum, anytime you all mess with velocity, right is positive, left is negative. Anytime you talk about rotation, I don't care what you pick. Make clockwise positive and counterclockwise negative. Just make certain you're consistent. Direction matters when it comes to vectors, and angular velocity is a vector. If you do not put this negative here, you can do everything else perfectly and it won't work. Your problem needs to match what's happening. These are not helping each other. When they come together, they're going to kind of fight. Which one's going to win? We'll find out. They're going to come together. One spinning one way, one spinning the other. When they come together, they're not going to both be spinning opposite directions now. They got to spin one velocity. One wins. The math is going to let us figure out which one wins. Very, very important. The math needs to match the reality. All right, we are solving for omega final. And I'm going to put this very simply. My beginning, you know what? Let's go ahead and do sum. My sum of my initial angular momentums must equal my sum of my final momentums. And I'll remind you that omega, or L equals omega times I. Try to set it up, y'all. This is the hard part. Can you set up? It's just like conservation of momentum. It's just like it, except everywhere there's an M, there's an I instead. Everywhere there's a B, there's an omega instead. It's just like conservation momentum. I mean, it is conservation momentum, angular momentum. So try to set it up, y'all. See if you can do it. That's the challenge. See if you can set up the equation for angular momentum. This will not be on your formula sheet. There will not be there will be this. What I wrote here is what you'll have. You will have to set it up. You will have to figure out what times do I have. All right, I'll let you. I did some quick math in my head. The answer is going to be it's going to spin clockwise.
Yeah.
There's your initial and there's your final picture. Hope that helps you.
Can you just add the moments of inertia like you just add that?
Only the same one. Yeah, that's a great point. Yeah, that's a very good point. Yeah.
The same shape?
Yeah, it doesn't even matter if they're the same shape. It doesn't matter. Nope, you just have it. Because moment of inertia is defined as a sum. To calculate moment of inertia? Yeah. So, someone asked the really good question, can I just add moment of inertia just like I can add masses? So remember in momentum, when things collide, we just add their masses together when they're stuck together? You can do the same thing here. Moment of inertia is just like mass. In fact, the definition for moment of inertia, that I, was the sum. So if you have two objects, a sphere and a cylinder, and they're rotating about the same axis, they get stuck together, assume they're rotating about the same axis. Yeah. Yep, you just add the moment of inertia, that's your new moment of inertia. Yeah, it's great. Moment of inertia not as bad as you think, you just got to break it into a bunch of small, like simple things. All right, so I hope if you're able to generate this, if you can generate this equation, the rest of the problem is cake. If not, this is a great problem to practice. So we have I1 omega 1 initial plus I2 omega 2 initial equals, that's my initial momentum, angular momentums, y'all. They're separated. So I just put it there. Equals I1 plus I2 times omega final. They get stuck together. This is just like a collision problem, an inelastic. This is the inelastic collision, but for rotating things. They get stuck together. Heck, if you want, I'll prove it like, sure, I wrote it this way, but let's just go ahead and prove you all that that works. I1 omega final plus I2 omega final. They're stuck together, y'all. They have to spin at the same rate. If they both have omega final in it, factor it out. Factor it out, and ta-da, you just prove that you can add angular momentums together. Yeah?
Is there any sort of separation problem with?
Sure. Let's see, is this next one a separation problem? No, the next one. And there should be some in the problem set. You have a kid on a merry-go-round, and they like hop off or something. Yeah, that'd be a separation. So the question was, is there any separation problems? This last one we could have, nah, let's been the same rate. A separation problem, the classic one is you have like one of those, you know those rides that like, you ever seen those at a playground, the ones that you, like, they don't even use them anymore. It's like the metal, it's almost like a merry-go-round, but it's really small, that metal spinning disc of death that you can hop on and spin really quickly. Yeah. So one, you can experience angular conservation, angular momentum. Start on the outside of that thing. If you move towards the inside, it'll start spinning faster and faster and faster. That's the thing. Otherwise, a separation problem with angular momentum would be if you were on one of those things but it's spinning and you hopped not directly off of it because you didn't change too much. You have to hop backwards to like the direction it's rotating, and it'll stop moving. If someone jumps on it when it's spinning, it'll slow down because you've increased moment of inertia. All right, so yeah, that one's not quite that, but all right, y'all, fairly straightforward at this point. The math is super easy. If I can do it in my head, then it's super easy. I avoid doing math in my head at all costs because I've been burned too many times. I've made too many mistakes. Looked like a fool. All right, so 10 plus negative 8 is 2. Pretty confident in that. So what's my, and look, I get a positive. That tells me it's spinning clockwise. We said clockwise is positive. Omega F equals 0.667. All right, y'all just did some quick algebra, nice and easy numbers. And you can see it is somewhere in between the two. The other guy won out because 2 times 5 is 10, that's bigger than negative 8. So that one had more angular momentum. So it wins. Alright. Anytime there's a collision, you lose some energy to friction. I mean, literally think about these things hitting each other. They're gonna like grind against each other, it may not be instant. I mean, a clutch. If you've ever driven a manual, if you slam it, like, if you do a slam, it's not a good experience. But angular momentum is conserved, even if you lose energy. That's one of the really cool things about this. Just like momentum, it didn't care if 2 cars smash each other and it's a wrecked, awful mess. I mean, that does matter because it's not good for people inside. But as far as momentum is concerned, it's still conserved, even if you lose a lot of energy. Now, we can calculate how much energy. It's really simple. Like, you may be like, how are we going to do that? How are we going to calculate the energy loss? That sounds really complicated. We are going to do it the same way if you had a normal collision problem, y'all. Remember, energy initial equals energy final. If energy is lost, Just add a work to the beginning, y'all. Or, if you prefer, remember this definition, y'all. The work done, the energy lost. Work is energy gained or lost. Work is energy gained or lost. That equals the change in energy. Energy final minus energy initial. So how much energy was lost? Just find how much energy we had at the end, subtract how much energy you started with. That's it. And then I'm going to let you all think, what kind of energy do we have? There's only 4 choices. I've literally only taught you 4 types of energy in this class. Rotational energy, rotational kinetic, translational kinetic, potential energy due to gravity, and potential energy due to a spring. There's way more than that, but that's all I've taught you, so it's going to be... So in this problem, I have things spinning. That's all they're doing. They're spinning. They could be above ground, sure. They stay above ground. They don't drop to the floor. So literally the only type of energy that changes in this problem is rotational kinetic energy. What kind of energy do they have? Work equals 1/2 I omega. You know what, let's write it a little bit different. Kinetic energy rotational initial. Nope, final. Minus kinetic energy rotation initial. What energy do I have finally? 1/2 I omega final squared. Minus, what do I have initially? 1/2 I1 omega 1 initial squared. Plus 1/2 I2. This looks worse than it is, y'all. These numbers are all really easy. All the numbers here are really nice and easy. What's my initial energy? I got 2 spinning objects. Add up their energies. What's the energy final? I got 1 spinning object. Find its energy. Subtract the 2 and you found how much energy was lost. This is going to be smaller than the other ones, y'all. You're going to get a negative answer. Why? Because you lost energy. The math will tell you you lost energy. I end with less than I started with. You'll find that out when you plug in numbers. I'm not going to bother with it because at this point it's just plugging stuff in. And I want to get to the last problem so y'all can be done then. The content today. What do you think, But yeah, check this out, y'all. Make sure you understand. I just said a conservation of energy. Energy initial, energy final. If they don't equal, you lost it. Where'd it go? Somewhere. Friction. Air resistance. Something. Alright. Last problem of the last teaching needs. I mean, I guess the review will look more like this, so I don't know how exciting this is, but it is, yeah.
Alright,
No, that's fine.
could you put that on just a second?
Yeah.
The I for the first, like the 1/2 I,
Yeah, so that's the total.
the total I?
That's I1 plus I2.
Oh, okay.
Yeah. Yeah, that's important. Because which I is it? They're together now. Yeah, so I can call this like I total, but I'll clarify that here so when you look at it later. That's a good question. Yeah. No, thanks for asking. I'm sure a few people also had the same question. Okay. Playground has a merry-go-round has a mass of 120 and a radius of 1.8 and rotating with an angular velocity of 0.5 revolutions per second. What is its angular velocity after a 22-kilogram child gets onto it by grabbing its outer edge? The child is initially at rest. And I give you the moment of inertia for a disk, because we're going to say this thing's a disk. Keep it simple. All right, so I have a disk. Here's my really nice disk. So good. Wow. Which way is it rotating? Let's just say clockwise. It really doesn't matter. So great. There it is. That's my initial. My final is a disk that's rotating with a kid on it. Ooh, there they are. And it's going to still rotate. The kid jumping on it's not going to make it stop rotating. It always rotates somewhat. Okay, so we have mass. A mass of the disk, 120 kilograms. We have the radius of the disk, 1.8 meters. We have initial Angular velocity of 0.5. Revs, oh, this is mean. Okay, I say this is mean. These units aren't good. There's a typo here that's subtle and you may not have even realized it.
Isn't it common?
Yeah, this says an angular velocity, but my units stink. Yeah, I'll have to check what the solution has. It used the word angular velocity. If it says angular velocity, your units better be radians per second, not revolutions per second. Revolutions per second is frequency. This needs to be angular frequency because it had the word angle in it. So we'll just fix that, assume that this was what they meant and they didn't want us to convert it. Okay, we got the mass of the kid. That's 22 kilograms. And we know it says the kid's originally at rest. We know their initial velocity is 0. And you're like, what? Why do we care about that? Look, if they're not moving, then they're not spinning. Kid. Sorry, what was the question? Yeah, that. Wait.
Radians.
Oh, yeah. Thank you. Radians per second. All right, we are solving for the final. They're getting stuck together, y'all. We're assuming they're stuck together. We're assuming that kid's not letting go. If they do let go, then it's another problem. All right, y'all. Shock and awe. Initial angular momentum equals final angular momentum. We don't care how long it takes that kid to hold on. As long as they're not dragging their feet on the ground, that adds some net torque and that complicates things. But assuming the kid kind of gets on there pretty good and gets settled in, we're good to go. All right, so I'm going to move some things over, give myself a little bit more room to kind of play with over here. And this is going to be one of those, we set it up, and then I have you enjoy solving it. So much fun. All right, y'all, try to set it up. I'll give you all a minute or two. Can you do it? What is my initial angular momentum? What's my final angular momentum? Should I set up the problem? Don't worry about solving it yet. Just try to set up the math, because that's where I'm going to leave you.
Isn't the eye different? Because it's when the kid jumps on, there's like a mass on the edge. And not
Oh, there is. Yeah, so what is their moment of inertia? So I'll set it up. I will set it up for you all, and I'll show you what it's going to be.
Thanks.
Yeah, that part I'll give you all. So we have the disk. I'm just going to call the disk 1. I don't want to keep writing the word disk. Here, we'll put D for disk. LD times omega D plus L kid plus omega kid equals L of disk plus L of kid times omega final. Great news! That second term goes away, so our life is a little easier. And then the question was, what the heck is the... Look, so like, the moment of inertia for the disk I gave you. Easy peasy. So we have the moment of inertia of the disk. That's no problem. That hasn't changed. What is the moment of inertia for the kid? We're going to treat this kid like a point mass. He's a single point in space. Where is that kid located? A distance r away. So here's how we're going to treat this kid, y'all. Sure, I drew him as a nice, pretty picture. Here's what the kid looks like. A blob. A blob located some radius away. The moment of inertia of a blob a radius away, the definition of moment of inertia is the sum of mr squared. Well, we can consider him as one blob. One blob with a mass m located a distance r away. So what is his moment of inertia? It's just mr squared. The moment of inertia of a single object located some distance away, if we just approximate them as a blob, we have to in this problem because there's no width to this kid. Good rule of thumb, it seems complicated, approximated to a sphere, a blob, a point, but that's, the running joke, y'all. Spherical cow and all that. This is something we always do as physicists. Take something complicated and make it simple. Approximate it. We approximate them as a single dot located a distance r away. The moment of inertia for any object located that is just mr squared. And at this point, it's easy peasy. Y'all just plug in numbers and do math. And math is the easiest part, hopefully, of any physics problem I'll solve. If math is not the easy part, you all have gotten into a hard field. Hopefully, you're all fairly fluent in algebra and all that kind of stuff, because you're going to be doing a lot of it. Welcome to the job, y'all. Just like, again, you all need to speak this is the language. You better be good, you better be fluent at it, otherwise you're gonna have a hard time conversing with others in the field. But it's fun. Math is fun. It lets you explore things. And that's it, y'all. Again, plug in numbers, do the math, eat whatever. But that's it. That's our class. At this point, review. Go through the previous study guides. First thing I'll do on Wednesday is just a summary of test 3, everything since test 2. I'll point out the key points. We'll spend all Wednesday doing that, and then Friday, Monday will just be, hey, here are things to remember. It's been a hot minute. Y'all got a week? You got more than a week. You got so much time. Spend it wisely on this class, other classes, whatever it may be. Do not wait till do not cram, y'all. It's way too much to cram. Not a good idea for your brain. You will regret it. Break it up.